We were talking about dipole-dipole interactions. We're talking about non-covalent interactions and how they influence the world around you. Our goal today is for you to be able to answer the questions: why doesn't oil mix with water? How do bubbles happen? What are cell membranes made out of anyway? And why is lard a solid while vegetable oil is a liquid? So we've got a lot of ground to cover. We're going to do our best. I wanted to say just briefly, we're going to, at the beginning, just categorize the non-covalent or intermolecular forces. You probably already know these. If you have questions about them, please ask, because otherwise we're not going to spend a huge amount of time in them. Instead, we'll spend most of our time on the practical applications. So, as I said last time, a dipole occurs because of a difference in electronegativity, an uneven sharing of electrons. And the most famousest of dipole-dipole interactions is the hydrogen bond. And the classic example of hydrogen bonding is in water. And so in water, liquid water, each oxygen is bonded to two hydrogens, and then each of those hydrogens is interacting with, the delta plus on the hydrogen is interacting with the delta minus on another oxygen. And so in this way, each oxygen in water, it's almost like it's surrounded by four hydrogens. Some of them it's covalently bound to, and others it's just interacting with. And I'm showing you a brief network of hydrogen bonding. Here, the lone pair on this oxygen, the delta minus on this oxygen is interacting with this hydrogen in water. Here, the other lone pair is interacting with this hydrogen. I'm not showing you the two hydrogens that this oxygen in the front would be hydrogen bound to, because otherwise the drawing would get too complicated. This oxygen's hydrogen bound to this hydrogen, and it would be hydrogen bound to another. And so each of these blue lines is a hydrogen bond, and each of the lone pairs would be involved in a hydrogen bond. And so you have this network of water molecules, each hydrogen bound to each other. Now, in ice, that hydrogen bond network is pretty rigid. It's not transient. They don't move around a lot. And you've seen this on the macroscopic scale if you've ever seen a snowflake land on you. You're seeing a crystalline structure that at its basis, if you zoomed in, would have something like this going on. Now in liquid water, of course, the molecules are moving around relative to each other. And that means that in the liquid state for water, the hydrogen bonds are transient and rapidly interchanging, rapidly exchanging even. And there is what we would call high entropy, meaning disorder, right? And it turns out to be even cooler than that. In water, it's pretty easy for water molecules to exchange hydrogens. So imagine this oxygen, which I'm going to label in pink, getting close enough to, red, green, colorblind folks, I'm sorry, we'll choose blue. Oxygen gets close to the hydrogen in blue, and eventually that bond becomes covalent, and then the pink oxygen will let go of one of these hydrogens to another water molecule, such that proton exchange in water is rapid. In fact, if you put a single molecule of hydronium in a bucket of water, it would instantly be completely unclear where the extra proton was, because the water molecules would all be trading it back and forth with each other. All right, so that's sort of important to our story later on. We're going to use hydrogen bonding as part of our explanation for why oil and water don't mix. But for right now, think of in solid ice, the hydrogen bonds are more rigid, much less transient, and there is much less entropy. Of course, dipole-dipole interactions can exist with any molecule that has a dipole. So I'll just, for example, this organic molecule acetone has a dipole, which I'm going to draw with our dipole symbol that looks like this. A positive end near the carbonyl, carbonyl carbon, a negative end near the carbonyl oxygen. And of course, those dipoles can line up with each other. One thing you should know about dipole-dipole interactions is they're highly distance dependent. I don't know, I'm making those words up. Distance dependent, meaning the closer the partial pluses and partial minuses are to each other, the stronger the interaction. The other thing you should know is that they are highly orientation dependent. That part should be obvious. The dipole is going to be better when the negative end of one dipole is near the positive end of the other, right? If they're not aligned in the right way, then you don't get as strong of an interaction. Any questions about that you want to ask? We'll have more to say about hydrogen bonding later when we talk about protein structure in 352, when we talk about nucleic acid structure in 352 as well. That's probably good enough for now. So we've done ion interactions, we've done dipole-dipole interactions. You can mix and match non-covalent interactions. So you can invent a new category. For example, last time we talked about ion-dipole interactions, which were our explanation for why salt dissolves in water. Because you replace an ion-ion interaction with many weaker, but overall, summed up, stronger ion-dipole interactions. And this may be a good time to just pause and reflect on what I told you last time, which is things that are spontaneous, things that happen, things that are downhill in energy, have free energy changes that are less than zero. That means downhill. And there are two complementary ways for a process to be downhill in energy. One is for the interactions that you form to be stronger than the interactions that you broke. So the first term that you'll remember from our free energy equation, and just don't worry because we're not going to be calculating free energies. It's just a framework for understanding how things are going to work. When you see delta H or enthalpy, you should think of it in terms of the strength of either the bonds or interactions that are formed in a process versus the strength of the bonds or interactions that you break in a process. So formed versus broken. If the interactions you form are stronger than the interactions you broke, enthalpy is negative, and that'll help delta H be negative. Okay, and we'll refer back to that when we talk about why reactions are downhill in energy. The second major contributor to whether a process is spontaneous or downhill is this concept of entropy, which you can think of as disorder, where if you look at the negative sign in front of it, you conclude that more disorder is favorable for spontaneous downhill processes. And so as we consider a process and whether it will happen, we need to consider two things. Are the interactions you formed stronger than the interactions you broke? And second thing is, does disorder increase? So let's just, and I'm not going to redraw the picture, but I want you to think back to what we talked about last time with salt dissolving. Consider the salt ions in the crystalline lattice of solid NaCl, and then consider afterwards when the salt is dissolved, okay? We talked about strength of interactions formed versus strength of interactions broken. In the dissolving of salt, you replace strong ion-ion interactions with less strong, but maybe overall compensating ion-dipole interactions. Yes? No? Totally confused? Got it? Okay. So maybe enthalpy there is either neutral or favorable, meaning maybe you only just barely compensate for the strength of the interactions that you lost, or maybe it's slightly favorable. What do you suppose with entropy? Does disorder, what do you think? Increases, decreases upon dissolving? This is such a boring question, I know. We're really going to talk about stuff other than salt in a minute, but entropy increases, right? So overall salt dissolving is favorable. Good. All right, we got bigger fish to fry than just salt. So now we want to talk about what are called induced dipoles. And we'll do this. This one is kind of a pain to say, because if you want to say the interaction between two induced dipoles, you say an induced dipole interaction, which is really lame and boring to say. There are some other terms for this. One of them is called London dispersion forces, and the other one is called van der Waals interactions, and these are all ways of saying the same thing. So to illustrate what one of these is, I'm telling you things you already know here, but I learned that people like hearing things they already know because it makes them feel smart. So just enjoy it. Let's talk about the interactions that are available to, say, a triglyceride. And we'll draw a triglyceride maybe like one of the ones we drew last time. So let's do a 2, 4, 6. Let's do a 16 carbon chain, 12, 14, 16. Let's have this one maybe have a double bond in it. Oops. 2, 4, 6, 8. And the double bonds between 9 and 10. Then 12, 14, 16. And then let's maybe let this one have 2 double bonds or something. 2, 4, 6, 8, 9, 10. And then I'm not sure how many carbons go after that. Hopefully that's an even number of carbons. Interestingly, in natural triglycerides, the fatty acid chains always have an even number of carbons for reasons you'll learn about in 352. All right, so what kinds of non-covalent interactions do you think are available to a triglyceride? You got any polar bonds in there? You got a few, right? There's some carbon-oxygen bonds, so there are some opportunity for dipole interactions, but not a whole lot. There are some polar CO bonds. But overall, you've mostly got non-polar CH and CC bonds. So that tells you that overall this molecule is relatively non-polar. Now, as you do problems in the study guide, you may have some early stage problems that are like, is this molecule polar or non-polar? And that's fine, but you may kind of wonder what the cutoff is for something that is polar versus non-polar. And there really isn't a good one. You just have to sort of do the experiment and see. One of the biggest standards for is it polar or not is, does it dissolve in water? And one of the ways you can tell whether something dissolves in water is generally you need a nitrogen or an oxygen for every 5 carbons. And actually, sometimes it's not enough just to have oxygens. You need at least some OH or NH bonds to be soluble in water. So if you look at this, clearly there's some polar CO bonds, but you would say not enough for that sort of rule of thumb that for every 5 carbons you want at least 1 oxygen or nitrogen, and you want it to be at least some of them to have CH bonds. So some of you were wondering, do I actually have to calculate that out, and how many OH or NH bonds do I actually need? again, this is just a rule of thumb. It's not a hard and fast rule. It's something to whether or not you can expect something to be soluble in water. So there are a few dipole-dipole interactions, but you would not expect this molecule to be able to hydrogen bond very well with water, right? Maybe some of the oxygens could act as hydrogen bond acceptors, lone pairs on those oxygens interacting with hydrogens from water. But for the most part, you got nothing. So when you don't have any dipole or ion interactions, what you're left with is something called an induced dipole. And let me just show you how this works. So I'm going to copy the triglyceride. We're going to imagine two triglycerides approaching each other. And I know you can't do that if you're using a pen and paper, and that's okay. That's why the notes are going to be made available. All right, when the two triglyceride molecules are not particularly close to each other, we'll use some gray shading to indicate that electron density is more or less evenly distributed, especially around these nonpolar tails, all right? So here's electron density just sort of evenly distributed in the nonpolar tails. We'll use the color, let's use the color red for electron-rich spots of our molecule. Like these oxygens are all electron-rich. And maybe we'll use the color blue for electron-poor. So we would expect the carbonyl carbons to be electron-poor. We would expect these carbons to be somewhat electron poor. But overall, you can see most of the molecule is like, right? So when one of these triglycerides approaches the other, and this is what an induced dipole means, as they approach each other, their electron clouds begin to influence each other. And this is because of something called electron-electron repulsion. Negative charges repel each other, right? And so the electrons start to move in what's called correlated ways. It's like they can see each other and they can account for each other, and they're mutually avoiding each other. Perhaps you have friends like that, where you mutually avoid each other. Electrons are that way. So what happens, and this is just a snapshot in time, at one period of time, the electrons in the triglyceride on top will lean away from the molecule below to create a surface on the bottom half that is partially positively charged. Why? Because the electrons are leaning in the other direction. I'm going to use red to indicate that the electrons are leaning this way towards the top of the molecule so that they can avoid the electrons on this other molecule below. And correspondingly, the electrons in the molecule below will lean towards the positive surface on the molecule above. And so you'll actually have a mutually complementary surface. There's actually attraction between the two molecules because their electrons are avoiding each other. It's kind of cool the way that works out. Now that's a snapshot in time. I don't mean to communicate that this side of the surface is always negatively charged and this side of the surface is always positively charged. No, it fluctuates. It goes back and forth. It's like the molecules induce temporary dipoles in each other. Does that make sense? Heard of that before, sort of, ish? Okay. So these induced dipole interactions, sorry, I'm realizing that some of these notes are going to be confusing later. For water solubility, that was just an aside. Okay, so let's talk about the strength of van der Waals or dispersion forces interactions. How is their strength related to structure? First, it's related to the ability of the molecules to get in close contact with each other. So I'm going to call this increased strength with increased what I'm going to call contact surface area. Okay? So the more molecules are able to contact each other and actually get surface area in contact, the stronger the interaction will be. There are some related principles. Maybe I shouldn't have numbered these because what I'm going to talk about here sort of follows from the concept of contact surface area. Principle 2 is shape matters, because some shapes can contact each other more closely than others, and I'm going to demonstrate that in a little bit. The other thing is that not only shape, but for triglycerides, fatty acid length matters. And that's because the more carbons you have in the chain, of course, the more surface area you have for the molecules to contact each other. All right, so what we're going to do now is just show you some things, some data on fatty acids and triglycerides, and give you a sense for how the composition of the fatty acid influences the triglyceride. What I'm going to show you is, I left these notes here over the weekend, and astonishingly, nobody took them. I'm kind of offended. You would have thought that that would have been really popular. All right. So just a couple of things. What I'm going to do is we're going to talk first about fatty acids, because I have data on fatty acid melting points so that you can see how the shape and the structure of the fatty acid relates to melting point. So again, this is a fatty acid 2, 4, 6, 8, 10, 12, 14, 16 carbons. I'm going to list here some saturated fatty acids without double bonds. Then I'm going to list here some unsaturated fatty acids. Now, somebody out there wants to know, do I expect you to memorize what I'm about to write? The answer is no. I'm showing you data, but scientists should be able to explain data. So I got to show you the data before we try to explain it. Here we're going to have number of carbons, and then I'm going to put here the melting point of the fatty acid, so you can see how its structure influences melting point. And why do we care about melting point? Because when you melt something, when you try to make it go from a solid to a liquid, the reason you're putting in heat is so that the molecules have enough kinetic energy. By the way, temperature is just molecular kinetic energy. So the molecules have enough kinetic energy so they can move around enough to overcome the attraction between molecules. And what is that attraction? In this case, it's the dispersion forces, the van der Waals interactions. So number of carbons, let's see, 12. We'll go 12, 16, 18, and 20. And the melting point for the 12 carbon fatty acid is 43C. Now, that may sound like it's not that hot, and it isn't if boiling is 100C, but if you've ever been to Europe and had to adjust to temperatures being in Celsius, 43C is pleasant to be outside or unpleasant? Unpleasant. You know that because 37C is your body temperature. So if you want to hang out and have it be 98 degrees outside, then you can call that pleasant. 43 would be above 100 for us, right? So this is a solid. Even the 12 carbon fatty acid chain is a solid at room temperature. As you go up in size, you need even hotter temperatures in order to melt the fatty acids. So these fatty acids would all be solids. Now, we're just going to do a couple of unsaturated fatty acids. I've got to tell you here where the double bond is and what its configuration is. We're just going to do 16 and 18. And I want you to see the dramatic change in melting temperature. So one double bond between carbons 9 and 10. That's this fatty acid right here in that triglyceride. The melting point drops from 63 degrees to 0. So you should have gasped. Let's try that again. The melting point drops to 0. There it is. Thank you. That's the appropriate response. You haven't changed the number of carbons, but you just put a single double bond in, and now this thing that was a solid before is a liquid, even down to the temperature of water, freezing, 0 degrees, okay? Dramatic. 18 carbons, you put in a single double bond, and it's now 13 degrees. If you put in 2, the melting temperature drops even lower to minus 12. This is now a liquid even in freezing time. And if you put in 3 double bonds, it gets even lower, although the impact appears to not be additive. Once you have 1 double bond, the additional double bonds don't make as much of a difference. Okay, so let's talk about why that is from the perspective of just the fatty acids. And what applies to the fatty acids also, you will see, applies to the triglycerides. So here is that 16 carbon fatty acid with no double bonds. And I want you to notice that here's something you need to know actually about molecules without double bonds. And this takes us into some of the stuff that we talk about in chapter 4. You learned that you can rotate around sigma bonds when we first talked about sigma bonds. And I showed you some examples of that, and I can't find the app anymore, so I won't show you. But you can rotate around sigma bonds. That allows these 2 chains to adopt shapes that will be perfectly complementary to each other. The chains are flexible, they can, and if they can be perfectly complementary to each other, they can get quite close to each other, and therefore you can get an extended surface of this induced dipole interaction that I told you about before, all right? And again, the stronger or the more intimate the contact surface area, the stronger the van der Waals or dispersion forces are, and therefore the more energy you have to put in to overcome something to have it melt, all right? Now, let's do one that has a single double bond. 2, 4, 6, 8, carbon 9 is the double bond, that's 10, 12, 14, 16. So this is our 9Z 16 carbon fatty acid. And one thing that you may not appreciate about double bonds is that you can't rotate around them. I'm going to zoom in on just one of these double bonds, and we're going to explain why you can't rotate around double bonds. If we're viewing the double bond from the side, you know that the pi bond consists of basically 2 p orbitals overlapping with each other. Oops. Side by side. Need to adjust the font on that one. Oh man, how do I do that? There we go. 2 p orbitals side by side. If I rotate carbon 1, and you have to do this in your mind because I don't have a good way of drawing it, but you can imagine if you put your molecular pincers on carbons 1 and 2, held carbon 1 in place, and then twisted carbon 2, what's that going to do to the side-by-side overlap of the p orbitals? They're going to be 90 degrees away from each other as you twist them. And you may not know this, but 90 degrees apart, separation of 90 degrees, means orbitals don't interact well. There's like a dot product, cosine, something or other in there. But basically, orbitals can only overlap when they're end on end, as in a sigma bond, or side by side. But if they're perpendicular to each other, you got nothing. So rotating would require the pi bond to break, and therefore rotation around pi bonds is not just slow, but at room temperature is not allowed, okay? as you increase the temperature, you can give the molecule enough energy so that it can rotate, and that requires you to temporarily break the pi bond. But for most of in biology, temperature is not high enough for that to happen. Okay, so first thing you need to understand about the unsaturated fatty acids is because of the double bond, they are less flexible. And that means that their surfaces can't adjust their shapes to become as mutually complementary as the molecule above. In other words, because of the double bond, unsaturated fatty acids can't get as close to each other. And therefore, their contact surface area is a little bit weaker, and the strength of the interaction is smaller. Okay? So the presence of a double bond makes it so the individual fatty acid chains can't get as close to each other. That decreases the strength of the van der Waals interaction, so you don't need as much energy in order to move the molecules apart. Make sense? It better, you're gonna have to explain it on the problem set, and I'll probably ask a question about it on the exam. So to summarize some things you already know from your day-to-day experience, if we had infinite time, I should have brought today, I have a supply of various fats and oils that I could show you and demonstrate what, that they're solids versus liquids. But I'll just show you the fatty acid composition. I don't know why we're suddenly writing in blue. Fatty acid composition of some common fats or oils that you'll have experience with. So the first is animal fat, or as we like to say in South Texas, manteca. And I'll list the composition of saturated fatty acids and unsaturated fatty acids within each of these. We'll just label them, and this isn't comprehensive here. The numbers don't add up to 100, but they're percentages, and what's not on the list will be things that we're just not worrying about. So for the saturated fatty acids, you got 14, 16, 18. For the unsaturated fatty acids, we'll focus on the 18 carbon with 1 double bond and the 18 carbon with 2 double bonds. And you'll see that for lard, it's about 1% 14, 25% 16, 15% 18. There's actually a 50% composition of the monounsaturated and about a 6% composition of the polyunsaturated. And you know from experience that animal fat is solid, right? You can buy it, you can scoop it, it doesn't pour unless you heat it up. So apparently having a significant percentage, not even a majority of saturated fatty acids is enough to make a triglyceride solid. Now olive oil, which you know is a liquid, has a much heavier composition of the unsaturated fat. It's a fatty acid. It's about 80% unsaturated, about 70% polyunsaturated, and then has only a small amount, maybe 10 or 11% of the saturated fatty acids. I told you that the difference between fats and oils was that fats are from animals and oils are from plants. It's not necessarily whether they're solids or liquids. And coconut oil is the great explanation of this. If you go to the store and you buy coconut oil, is it a solid or a liquid? Well, it depends on what the temperature is outside, right? If it's really hot and the store isn't air conditioned, it may be a little bit liquid. But yeah, if it's just sitting on your shelf and your house is like 25 degrees Celsius or about 68 Fahrenheit, probably a solid. And that is because coconut oil, interestingly, and I don't have the breakdown in terms of number of carbons, but is about 86% saturated fatty acids, about 7% unsaturated. All right. There's so much to tell you, and we haven't yet talked about membranes and why bubbles are. I think we can do it in 10 minutes. One thing I do want to say, though, is What's the deal with oil going rancid? Have you ever eaten an oil or a food product that was expired? You know what that smell is? Okay. Some of you maybe served missions in equatorial climates and you carried around a little bottle of consecrated oil for the whole 2 years, and then you got back and somebody asked for a blessing, and then you opened that thing up and it was like, whoa, right? Does that ever happen to you? Oil, unsaturated fatty acids are not that shelf stable. Anybody know why? You don't. I'm here to tell you. Yeah, go ahead. Yeah, double bonds, right? Homo, LUMO, double bonds have higher energy electrons. They're more reactive. So double bonds in the fatty acid chains will react with oxygen, and that creates a change in taste and smell in the oil that we call rancidity. Sometime I need to tell you about the rancid tostada shells of 2016 and Sunday dinner at my mom's house, but today is not that day. So, in fact, having told you the title of the story, you basically get the gist. So I think we're probably good on that. Right, and that lets you, the concept of oil rancidity allows you to understand why you can read on some food labels the words hydrogenated. You ever seen that before? Sometimes it's partially hydrogenated soybean oil or hydrogenated soybean oil. The food industry knows that oil goes rancid, and so it used to be one of the things they would do to prevent that from happening would be to do a chemical reaction on the triglycerides so that the double bonds would go away. You can take this molecule that has one double bond and you can expose it to hydrogen and a metal catalyst, and that will reduce the double bond to be an alkane. You're going to add 2, 4, 6, 8, 10, 12, 14, 16. You're going to add hydrogen across the pi bond. Suddenly that becomes saturated. It's now going to be a solid, and it's also going to be more shelf stable. Problem is that saturated fats are not that good for you, and so over time debate's gone back and forth, but there's more to the story that I could tell you that we don't have time for. Maybe we'll pick it back up when we get to triglycerides in 352. All right, yes?
So looking at animal fat versus olive oil, animal fat, like altogether, it's going to be like 1% saturated, just adding it all up. But it still looks like the majority is unsaturated.
Right, the majority is unsaturated, but apparently even having that 40-ish% saturated is enough to make it a solid. Yep. And we'll talk maybe in 352 about why triglycerides are the choice for energy storage in biology. There's an interesting story there that we'll maybe pick up back in 352. All right, so I got like 5 minutes and I need to explain oil, I need to explain soap, membranes, and bubbles. Are you ready? Yes, let's do it. Okay, so let's look at a fatty acid. We'll draw the 16 carbon fatty acid again. And 2, 4, 6, 8, 10, 12, 14, 16. We're going to draw it in the form in which it would exist at physiological or pH 7. The carboxylic acid with a pK of 4 is going to lose its proton. The group at the end of the chain, the carboxylic acid, is going to be relatively polar and relatively electron rich. So this is very capable of ion-dipole interactions, and it's also capable of being in water. It's that particular portion of the molecule has water solubility. Now, the nonpolar tail here, the part that I will highlight in gray, is not water soluble. It's nonpolar. It can't interact with water. So what happens is the molecule will associate with other molecules to try to minimize its exposure to water. I need to tell you the story of why oil and water don't mix. I told you we would do that today. it's pretty obvious that they don't mix. And so to finish these stories today, we're not going to spend time talking about it, but I will tell it to you at the beginning of class next time. If you notice, this fatty acid has sort of a conical shape. It's got a polar head group and a nonpolar tail. And if the molecule starts to associate with other copies of itself, they can associate side by side, and there's curvature to their association. The nonpolar tails stay in the inside where they can avoid exposure to water. This is not going the way I planned. All right, let's try this. Now we're going to copy the 3. And over time, you get a sphere that is sort of like an M&M. It's got a candy-coated shell and a chocolate interior, only this case the shell is polar head groups and the interior is nonpolar tails. And you end up with this structure that's called a micelle. And this is how soap works. So on the exterior of the micelle, you've got water, which I'm representing with blue, because why not? All right, and the polar head groups are okay interacting with water, but then you have this nonpolar interior, and if you have, sorry, I'm not going to attempt to draw a grease molecule. We'll just say if you have grease, that gets, oh, come on. There we go. That gets packaged in the interior of the micelle and is suddenly water soluble where it wouldn't be before. Okay? So the first soaps that humans made were all fatty acids. They got them from triglycerides, and they got them by breaking the ester bonds in the triglyceride to liberate the fatty acids. We'll talk maybe in 352 about that reaction and how it happens. Okay? So soap works because the fatty acid itself, the molecule that's a soap, has a conical shape, and when it associates side by side to avoid exposing the nonpolar area to water, it forms this sphere with a nonpolar interior and a polar head group. You got that? Okay, let's talk about bubbles. Now, the structure of a bubble. If you've ever blown bubbles, you've got air on the outside and air on the inside, and a thin film composed of water and soap that separates the two. Okay? Based on what you know about one of these fatty acid molecules, tell me what that thin film looks like. Where should the polar head group be in a bubble? Should it be exposed to air or should it be exposed to water? Water. It's more preferable for the the nonpolar stuff avoids water so much that it would rather be sticking out into air than be in the water. So actually, if you think about what the structure of a bubble is, you have this thin film of water molecules, and then you have, oh man, that was ineffective. I needed to copy. Running out of time. I'm okay taking more time on this than I intended because this is actually the fun stuff of chemistry. This is how you learn about how the world interacts, how the world works around you. And someday when you're blowing bubbles with the kids in nursery or with your own children, you can be explaining this to them. And they will appreciate it. So you've got in the thin film of a bubble, you have sort of 2 layers of soap molecules, some of the nonpolar tails of which are exposed to the air. And then the interior, you've got this thin layer of water. And that is a bubble. Behold. All right. I still need to tell you what? I need to tell you why oil and water don't mix, and I need to tell you about cell membranes. The cell membrane story is short, and the why oil and water don't mix story is short. I think that'll be 10 minutes of next time. Otherwise, we're moving on to chapter 4. So I will see you on Wednesday.